Okay, so let me just make a very quick introduction to the Sambamurti Memorial Lectureship. It was established in 1992 by the family and friends of Adit Sambamurti. He was a young physicist here at the lab who died tragically. He got sick and died at the age of 31. And his family then figured out what they wanted to do. They wanted to have some sort of memorial, and they came up with this idea. It's a lectureship that honors work by a young, high-energy or heavy-ion experimentalist, preferably in the areas of Adit's interest. There's a monetary award if they turn in the written version. And the lecture is to be to students working at Brookhaven in the summer on the work for which the recipient's being honored. And as I mentioned, there's a written version involved or desired. The lectureship is administered by the B&L Physics Department through a committee. The committee members are Chellis Chasman, myself, Serban Protopopescu, and Mike Tannenbaum. I have here a list of the previous lectures. This is actually now, I think, the 22nd of these lectures, so time goes by very fast. So some of these names you'll recognize. They've become quite prominent in the field. We tended to get them before they were prominent, so I guess we had pretty good judgment. We tried to aim for a person who managed to achieve something, and that's no joke in today's, to become outstanding in today's very large collaborations, and yet to be young enough to communicate with the students and sort of remember what it was like to be a student. This year, the award goes to Elliot Lipeles of the University of Pennsylvania for his contributions to the discovery of the Higgs boson. The title of his talk today is The Higgs Discovery, How It Happened and What It Means.
Okay, so let me just thank you for the introduction, and it's a privilege to be here and be in that list of names. Okay. So I'm going to talk today about the Higgs discovery, which I think that many of you have heard about. I work on the ATLAS experiment at the Large Hadron Collider, which was one of the places where the Higgs was discovered. And so I'll start with what is the LHC and a general idea of why we're building these big colliders, and give you some sense of scale about how big the LHC is. And then talk about what we're looking for, what we found, and then give you some idea of what the next steps are in this pursuit. Okay, so the first thing is the Large Hadron Collider is a very large experiment. It's an experiment where what we do is we collide protons with protons. There are several experiments, two of which are focused on looking for the Higgs. CMS and ATLAS. I work on ATLAS. I used to work on CMS, so I'm kind of a traitor to some people anyway. To give you a sense of scale, this is the airport in Geneva. That's Mont Blanc, the tallest mountain in Europe. In Western Europe, depending on who you ask. And this is Lake Geneva here. Another way to get a relative sense of size, this is the RIC, how big the RIC ring is compared to the LHC. The other thing to notice different between RIC and the LHC is the LHC is actually underneath the ground, going under houses in the French countryside. This is the French-Swiss border, this dotted line here. The main site that's equivalent where the offices and conference rooms and halls like what we're standing in now would be at CERN is over here. You'll notice like the CMS experiment is a 9-kilometer drive across the center of the ring through the French countryside and across an international border. ATLAS has the privilege of being right next to the main site. There's also a specialized heavy ion experiment here, ALICE, and for 1 month out of the year, or 1 to 2 months, we do lead-lead collisions, doing similar physics to what's done here with RIC. I don't participate in that, but I thought I would mention that and give people an idea of this. Okay, so here's another view of what the ring looks like, and you'll notice here that the ring is underneath the ground. It's about 50 to 100 meters vertical down below the ground, and 27 kilometers in circumference. And you'll see that there's other bits over here, and what these are is that it takes several steps to inject the protons and get them up to the full energy. And I'll describe that a little bit more as we go on, before we collide them at these very high energies. And so this is a picture inside the tunnel. You can see these big blue things are the magnets that keep the protons moving in circles. And here you see the complicated plumbing that goes on inside of here because it's superconducting, so it has a superfluid helium that keeps the magnets cold. It's also got superconducting interconnects between the magnets to carry the currents that power the magnets. There was a major problem with these back in 2009, but we recovered. And then you can also see for fun, this is how you get around the tunnel. By bike is preferable. There's also electric carts if you have heavier equipment to move around. I don't actually spend a lot of time in the tunnel. There's a whole extra set of experts who focus on building the accelerators. There's probably some people who do that kind of work here as well. So why high energy collisions? And basically the answer why high energy collisions is because E equals mc squared. So when you think about it, it's like colliding two pinballs and getting out two bowling balls. That's the idea. So you're taking a very, very high energy, you make this big high energy collision, and now that energy by E equals mc squared, energy equals mass times the speed of light squared, you get high energy particles. You can make new high mass particles out. That's the fundamental reason why you have a high energy collider. To give you a sense of what E equals mc squared really means, because you don't think about energy turning into mass very often, a nice little example here is if you have a liter of water at room temperature, it weighs a kilogram, about 2.2 pounds. At room temperature, if you now heat it up on the stove to boiling and you don't lose any of the water going out the spout or anything, which of course would really happen if you did this, but you don't lose any of the water, that same liter of water is going to weigh 3 nanograms more. So it gains just a little bit of mass. But now we're talking not about raising something to the temperature of boiling, but to a very, very high energy. And that's why we build these colliders. So how high energy? Well, the unit we use is an electron volt. And this is 8 trillion electron volts is the energy of the LHC right now. And so 0.5 electron volts would be the energy that an electron would get going from one end of a AA battery to the other end of a AA battery. And so to put a scale on that, if you want 8 trillion electron volts, what you need is to line up 5.3 trillion AA batteries end to end. And in fact, in 2015, we're going to go up to 13 TeV. So another way to get a sense of scale here is that to make one proton, you need 1 billion electron volts. And to make a Higgs particle, you need 25 billion electron volts. You'll notice that this is only billion, and we have 8 trillion. So why do we need so much more energy? Well, I'll come back to that in a bit. In fact, we need an energy significantly higher than the energy we need to make the Higgs itself, as it turns out. So why is it a ring? Well, lining up Duracell batteries like this would not be a very effective way to build a device. It would be almost twice the distance to the sun to get to this energy, so that's not practical. So instead what we do is we have the protons circle around in a ring. The protons travel around 11,000 times per second. They accelerate to 8 TeV in about an hour. So it's a slow raising of the energy. They basically get a little push every time they go around, gaining only 200,000 electron volts in every turn, and they end up traveling in that time, in that hour, 7.2 times the distance to the sun. So they're going a long way. They're slowly raising their energy up to the energy that we want for collisions. So another way to get a sense of scale, and I think this is my favorite example, is that inside the ring, we don't just accelerate one proton at a time. We accelerate a little bunch, and we actually have a chain of little bunches. So we have 1,380 chains of these little bunches of protons. And if you add them all up, it ends up being about 100 billion protons, which is about 1 billionth of a grain of sand. So you take this 1 billionth of a grain of sand, and you accelerate it up to 8 TeV per proton. So each proton in there has 8 trillion electron volts. It ends up, if you do the math, that it has that little 1 billionth of a grain of sand has the kinetic energy of a car moving 25 miles an hour. So when we dump the beam, so sometimes you ramp up the energy of the beam, and eventually when you're done with it, you send it into this thing called a beam dump where you get rid of it. That beam dump is essentially getting hit by a car moving 25 miles an hour when this happens, when this beam hits it. So it's a pretty big wallop for something that you can't even see, right? Okay, so I wanted to add a little bit about the procedure of how the data is collected, because I often get a lot of questions about this. So the way this works is you start with the machine empty. So you have a big, long tunnel with a vacuated tube. There's nothing in the tube. The magnets are all off. The first thing you do is you turn on the magnets to this low energy that you're going to inject the beam at. So you have other accelerators down the line that get the protons ready at a low energy to be put in. And this is low not by our normal standards, but low by LHC standards. It's still a large energy. The next step is you put in one proton beam, then you put in the other proton beam, then you ramp the energy. So what this plot is showing you, if I step back here, the blue and red lines here correspond to the left axis, and it's the amount of charge, the total number of protons in the beam. And then the black line is the current in the magnets, and the current in the magnets is directly proportional to the energy that you can achieve. So this is the energy in the magnet. Whoop. I'm not doing very well. Okay. So right here, the black line goes up. We've ramped the magnet energy up. So at this point, we have the beams at a very high energy, and they start colliding. And slowly, particles fall out of the beams, partly because they're colliding and partly because we're not perfect in keeping them in the beams. And so you see that the intensity, these lines are dropping down. Slowly, the intensity of the two beams drops down. Eventually, it drops down far enough that we don't have as much as we used to have. And so we decide that we want to stop and refill. And so then what you do, there's the slow decline, is you dump the beams, you drop them out, you put them in this beam dump. It gets hit by this 25-mile-an-hour car, essentially worth of energy. And then you turn off the magnets and you start all over again. Okay. So now let's go back to E equals mc squared. Remember, we're colliding these pinballs, these little tiny protons, and we're trying to make new heavy exotic particles that we want to study. But E equals mc squared also goes the other direction. So now they decay. These new heavy particles are going to immediately fall back apart into little simple particles that we already know. For instance, protons or electrons. So here my two pinballs come in. They make these two massive exotic particles that you don't see very often. But these heavy exotic particles, they fall apart into these little, into these other particles, right? And that are, again, the standard particles that you know. So you have your two protons coming in, and these might be electrons over here. So you have common particles coming out. But it's important to know that because this bowling ball had a lot of energy, these guys are going to have a lot of energy, right? It had a lot of mass. The mass is energy, and that becomes the very high energy particles coming out. So there's one more complication to talk about, which is that we're not colliding fundamental particles. We're not actually colliding little tiny specks of matter that are fundamental. We're colliding protons and neutrons, or protons, and we know that protons are not fundamental particles. They're made up of these things called quarks. So you're all familiar with atoms being made up of nuclei, and the nuclei in turn is being made of protons and neutrons. I suspect most people know that protons and neutrons are made of quarks. And so really, it's these quarks that are colliding, but they're inside these protons. So really what we're doing is we're colliding a sack of pinballs with another sack of pinballs, right? And so this is why you need so much more beam energy than you actually get out in your collision, because some of the energy is distributed all over the whole sack of pinballs, but we only get one to collide with one at the same time. The other ones kind of scatter off each other very gently, and they make a big spray of these other light particles coming out. So you get lots of protons and neutrons and particles called pions and kaons coming out of low energy. And then you have the particles that make the new exotic heavy particles coming out. And when they decay to high energy particles. And so we have these two high energy, or four high energy in my diagram, particles coming out, and then lots of low energy particles. So what this looks like is here's a picture of a real collision. This is actually from the competing experiment to my experiment, CMS, but I like the picture. In this diagram, the beams would be going along this axis here. So one proton beam would come in this way, one proton beam would come in this way. They collide, they make a big spray of particles. The lots of little ones that didn't collide very strongly are making this spray of yellow lines here that are the light particles coming out. But the heavy particles that you produced, they decay into very high energy things coming out. And those high energy things are these green things here. And so what we need for this whole complicated thing coming out, all this spray of particles, is we need a detector that's going to go measure and figure out which ones were high energy, which ones were low energy, exactly how high energy were they, things like that. And so what we have is a large detector. This is the detector that I work with. I didn't actually have a big role in assembling it. I'll mention what my role was in a little bit. For a sense of scale, these are people. Here, this is with a beam line. So one set of protons comes in here, one set of protons comes in here. They collide right in the middle. Then they emerge, and they go through this sort of onion skin of various very sensitive detectors. And what you end up with is a picture of each collision. And so what the detector is telling us is the directions and energies of all the particles that are coming out. For a little bit more detail, I've made a slice. Here's a slice of the detector. So if I take this detector and I just make a little tiny piece of it just to show the various layers in a little bit more detail, here the proton beams would coming in and out of the board, colliding right in the middle. The spray of particles comes out this way. And there's many layers. The first layer here is a pixel detector. And a pixel detector is actually very similar to the technology inside of your camera. So you have a camera that has what's called a CCD, a charge collection device. It's a very similar technology, except that your camera takes pictures like 1 per second. And this takes pictures at 40 million times a second. And it has a lot more pixels than your camera. And then as you go out, you just need larger and larger devices because the particles are spreading out as they go farther out. So now the silicon strip detector has little long strips rather than little tiny pixels like your camera. There's a gas-based device called the transition radiation detector here. And what all these devices are doing is they're measuring the trajectory of charged particles. They can't see neutral particles. That's the way the technology works. They only see charged particles. And then we have 2 more devices out here which can measure the presence of neutral and charged particles. The first one detects more electromagnetic particles like the photon and the electron. And the second one detects more heavy hadronically interacting or strong force interacting particles like the proton and the neutron. And by the pattern of whether it's seen in each of these different detectors, you can begin to classify each particle that emerged as that was an electron that came out, went this direction with this energy. That was a photon, came out with this direction and this energy, etc. Okay, so the final step in how the detector operations works is something called triggering. So what triggering is that the collisions in ATLAS happen 20 million times per second. So ATLAS is able to make a picture 20 million times a second, but we can't possibly afford to store that much information, that many pictures. It's just way too many. It would fill up your hard drive in seconds. So instead what we do is we select the most interesting ones to keep. So you have this giant stack of pictures, and you're selecting the most interesting ones. If you select the wrong ones and you throw out the interesting ones, then you're not going to find your Higgs particle. You're not going to find anything. So it's a key feature to figure out how you're going to make a very fast decision to go from the large stack to the little stack. So that's what we call triggering. That's the role I play is I work in the trigger group along with, I think there's now almost 500 people involved in just the triggering aspect of the detector. So it's a very large enterprise. Many colleagues, there are many people here who work on the trigger as well at Brookhaven. Okay, so now I just wanted to give you a little summary video because they have a very cool PR video from CERN. It's about a minute long to summarize what I've just told you. So the way this starts is the protons start in a little accelerator. They go around a series of larger and larger accelerators, slowly picking up energy. Each one is very similar to the ones, the LHC that I described, except they're smaller. Now you're getting into bigger ones. And then finally you get into the LHC, which is the largest ring. And the protons circle around inside the 27-kilometer-long tunnel. Here the blue things are, again, the magnets that keep the protons bending in a circle. And in a second here, we're going to go inside the actual beam pipe, which is a vacuum, where the proton beam is. There's many little protons in a bunch. Again, the proton is full of little quarks. And so as it goes around, it's going to come around and it's going to hit inside the detector, a head-on collision with a proton going the other direction. And out comes this big spray of particles. And now the detector records information about the energies and directions of all the particles coming out. Okay? So now I've told you a little story about what we're doing. We're making these collisions. Well, why are we doing it? Right? That's the next step. What are we actually looking for? Or what were we actually looking for? And what are we going to be looking for in the future? So in order to do that, I need to tell you a little bit about the fundamental forces of nature. I think you've probably heard the names of them at least, but I'll give you a little bit of description of them and tell you what, in particular, what role the Higgs plays in them. So the forces are electromagnetism, weak, strong, and gravitation. As it turns out, electromagnetism plays by far the largest role in your daily life. Almost everything you do is electromagnetism. Gravity plays a little bit of role. Of course, you know what role gravity plays. It keeps me here on the ground. Gravity is actually a very weak force. It's extremely small, and it takes the entire Earth to hold me down right now, whereas there's a very thin little layer of atoms underneath my feet that's holding me up. And that layer is sitting on top of another layer, sitting on top of another layer, but each one is holding me up. Like you just need a tiny little layer. It's a much stronger force. In addition to the ground holding me up, electromagnetism describes magnets, as you might guess from the name magnetism. It describes the atom, and therefore everything that follows on from the atom, including most of chemistry, most of biology, many, many things like that, all follow on. They're all electromagnetic effects. Light is also an electromagnetic effect. So you might be amazed to hear that all of these things are really just one force in my table, right? But that's the main goal of physics, or one of the main goals of physics, is to simplify and combine things and to unify different phenomena into single phenomena, to understand how they all fit together. And as it turns out, you can find more and more simple theories. So unification and symmetry play a central role. And so you can go back, and this is physics that was done about 100 years ago, that magnetism, electricity, and light were all unified with an understanding of special relativity into this one theory we call electromagnetism. So before you understood special relativity, you wouldn't have known that these were all the same thing. People were beginning to understand that they were all related, and it was really special relativity that congealed it all together. And so you end up with this single theory in the end. Okay, so that's the end of electromagnetism and the mention of what unification means. The next thing is the strong force. So remember, we have these nuclei and these protons and neutrons, but they're charged particles in here, and you guys all probably know that if I have two charged particles, they want to repel each other. So what holds them together in the nucleus? Well, what holds them together in the nucleus is the strong force. So there's strong force holding these protons in, because otherwise they'd want to fly apart in opposite directions. And in fact, it turns out that the strong force has an appropriate name. It is much stronger than the electromagnetic force. And so it turns out that this nucleus is 10 to the 5 times smaller than the atom. It's way tiny little dot. Like you see this picture like this, it's not really like that, because if this was drawn to scale, the dot in the middle would be too small to see. Okay, and the final force, or the next force I want to talk about, is the weak force. The weak force doesn't play a very obvious role, but one important place it plays is in the burning of the sun. So I'll describe that, where the sun is full of lots of protons that came from the early universe, and you had clouds of gas that eventually condensed down into these balls of hot gas. And so how does it burn? Well, it burns by taking two protons, going through the weak interaction into a proton and a neutron, or a deuterium, and releasing a positron and a neutrino out. So this special process is the first step of the burning of the sun. And to give you an idea why it's called the weak force, if you consider this neutrino guy, it only interacts via the weak force. The positron interacts via weak and electromagnetic. The protons and neutrons and the quarks inside them interact by weak, electromagnetic, and strong forces. So this guy, the neutrino, only interacts weakly. And how weakly is weakly? Well, the neutrinos that are being produced in the sun from this burning process, they go straight through the Earth. No problem. Just all the way through the Earth. Very, very rarely do they interact. And in fact, there's another class of experiments that build detectors in giant mine shafts way underground. And they have to be very, very large detectors, because these guys interact very rarely. But every once in a while, one will interact, and you'll be able to see its interaction if you have enough shielding. And here you're essentially using the entire Earth as a shield, just to hide all the other things that could be there, so that only the neutrinos get through. Okay, the final force in the list is gravity. And we don't really have a good theory for gravity on very, very small scales. So obviously we have gravity on the scale that we exist on. We know how to describe that physics. And we can actually describe it on larger scales and somewhat smaller scales. But if I had a very, very large hadron collider, 10 to the 16 times larger than the LHC, I would have a problem, because I would not know how to include gravity in my description of that collision. I would have no idea where to start, essentially. So that is an outstanding problem in physics that doesn't currently have a solution, although there are many ideas. So where does the Higgs come into this story? The Higgs comes into this story because it allows us to merge electromagnetism with the weak force. Or really, what it turns out is that at high energies, there's only one force, electroweak. And that what the Higgs does is it separates it out into two forces at lower energy. So it's called a symmetry breaker, because it takes two things that are really the same and it makes them look different. Another way to look at that, and this is getting a little more explicit for people who maybe know a little bit already, is that before the symmetry breaking, you have three identical and one other force carrier. So the force carrier, something like the photon, is the force carrier of the electromagnetic force. It's what exchanges. When I have two electrons come in, bounce off each other, and go away, you can think about a photon going between the two. That's what we mean by a force carrier. So before the symmetry breaking, you have three identical W1s and one called a B1. And then you can have this symmetry breaking, and this work is done by the Higgs, this breaking aspect. And you get four different kinds of force carriers. And we actually, when we do nuclear physics, we're experiencing these kinds of force carriers, not these guys. And what was interesting, this theory's been around for a while, and we've known it was right for a while because there's a deep relationship between the masses of these W and Z particles and the strength of the weak and electromagnetic forces. So that was already tested. So we already knew there was this symmetry, but we didn't know what was breaking the symmetry until we found the Higgs. Right? The Higgs was there in the model. People were looking for it because we had a theory that, oh, if this Higgs particle existed, it could break the symmetry, but we didn't know that it broke the symmetry. So now we found the Higgs particle. We're pretty sure, and we're still on the confirming that it's the guy who breaks the symmetry, but it was exactly where it was expected to be the guy who does that. So the other thing that you probably heard about, because you probably heard in the media about Higgs and mass, and as I just mentioned, mass plays an important role in this whole symmetry story. You probably heard that the Higgs gives mass to all particles. So let me give you a short story about how that happens. So the way it works is that it breaks this symmetry by giving masses to some of the particles and not other particles. And the way it works is that there's this thing called a Higgs field. If you're familiar with the electromagnetic field or the electric field, you can think an electric field has a value at every point, has a value in a direction at every point, right? And the Higgs field is similar to that. It has a value at every point in space. But the trick is that it's set up such that if it had a zero value, it takes more energy than it has if it has a non-zero value. So this is the energy in this direction, and this is the value. It turns out it has two different values at every point. So what this plot is saying is it's like a hill. There's a potential energy. If you had no Higgs value at some point, then it would take more energy than having a Higgs value at some point. So what you end up with is that you have this Higgs field, and it has a value at every point in space. It's so that now space is full of the Higgs field. Everywhere there's some value of this Higgs field, some amount of energy bound up in every little volume of space. Now, what happens if I add a particle that couples to the Higgs field is it kind of pushes the Higgs field out of the way. And as it pushes that Higgs field out of the way, or manipulates the Higgs field, it moves it away from the lowest energy value. So it takes energy to make a particle because it's pushing this Higgs field around. And that energy is bound up next to the particle as potential energy. And because of E equals mc squared, that means the particle gets a mass. There's energy bound up by pushing away the Higgs field, and that is what's giving particles mass. The Higgs particle itself is a wave in that field. So there's this field everywhere. The Higgs particle is a wave in that field, and that's what we're now looking for. That would be our confirmation that this field is out there, is that we see this Higgs particle. So, okay, why was the Higgs particle so hard to find? This is kind of an interesting story. Remember, I just told you that anything that couples to the Higgs field gets a mass because it pushes the Higgs field out of the way. The more it couples to the Higgs field, the more it pushes the Higgs field out of the way, the heavier it is. So that means that any particle that couples to the Higgs field well is going to be heavy. But heavy particles decay. Remember, I told you if I make a new heavy particle, it's going to decay into two light particles, right? And so any heavy particle is going to decay, and we can only collide things that are stable enough to put them in an accelerator, run them around in a circle for an hour until I get up to a high energy, and then collide them. So there's a fundamental problem here. I can't collide anything that couples to a Higgs. So the solution is a little tricky. This is maybe a little bit for experts, but I'll describe it a little bit, try to make sure everybody can get an idea. So these are what are called Feynman diagrams, and these are the processes that we look for. So you can think about it as the x-axis here, or the vertical axis here, is separation in space, and the horizontal axis is time. And so this picture depicts two gluons coming through, making two top quarks, which then annihilate each other into a Higgs boson. The top quark is very heavy. It couples well to the Higgs. And also the strong force is very strong, so the top quark couples very well with the gluons. So this actually turns out to be the biggest process in producing these things, in producing the Higgs. Now, the tricky thing here is that you might, if you know a little bit, you might know that these two top quarks, each top quark is actually heavier than the Higgs. So how can I produce two Higgses, two top quarks that are heavy, and then have them give away energy to go down to the Higgs mass? The reality is that quantum mechanics allows you to play that game. If you're familiar with tunneling in quantum mechanics, you can actually have a particle go through a potential barrier that it can't go over. It's a strange phenomenon, but if you have a wall, in quantum mechanics, a particle can go through the wall without actually going over the top of the wall. These processes are a little bit like that. Another way you can do this is you can collide two quarks, produce a W particle, and then have that W particle go to another W particle and a Higgs. And the reason that you should know that this has to violate energy is because I can't have a particle with one mass go to a particle and itself, right? Because then the masses can't add up. I can't have a particle go to itself and a Higgs and have the particles, all the masses add up to its own mass. And then this is the final diagram I won't describe in detail. But the problem with all these processes is they're very rare. And because they're very rare, we need lots of data in order to find them. Okay. So the next step in the discovery process is now that I've produced this heavy Higgs particle. Remember, I've collided my pinballs, which are the quarks or the gluons, and I've produced a Higgs particle, and now that Higgs particle decays. It's this heavy bowling ball, right? And it wants to go back to the light pinballs. So it decays. And because quantum mechanics is a probabilistic theory, it can decay in many different ways. And this is a pie chart of how often it decays to each thing. So quantum mechanics doesn't tell you what each Higgs is going to decay to, but it tells you how often it decays to each different thing with very high precision. So here's what we expect the Higgs particle to decay to. You'll notice it's a very complicated wedge. The biggest one is BB bar, but it turns out it's very hard to identify B quarks in the detector. WW is there. It's fairly big, but it's also not easy to figure out in the detector. That's actually the one I worked on. ZZ is more rare, but that's now been seen. And finally, gamma gamma, which I'll describe to you in a minute, is so small that it's actually in this wedge of other. And it turns out that these three methods are about equal in their sensitivity. This just has to do with the magic of exactly what mass the Higgs was found at. If it was found at a different mass, if it was found lighter, then gamma gamma would have been better than the other ones. And if it was found heavier, WW would have been better than the other ones. But at the mass it was found at, turns out all three are about equal. We're still searching for these other processes. It's very interesting to see if this pie chart is exactly what we think it is. So far we've measured in this pie chart a little slice in the other category, this orange thing and this red thing, but we don't know any of the other pieces, right? So we want to measure that whole pie chart. So again, another process that we're still searching for is mu mu, and really intriguing to me and what I'm now directing myself towards, and I know some people here at the lab are also working on, is looking for Higgs decaying to dark matter, which is an intriguing possibility. Okay, so now I've produced this Higgs particle, and it decays to two photons, gamma gamma, which is two photons, two particles of light. How do I know that I've seen a Higgs? So here again is a detector diagram of what an event looks like. Beams coming one way, beams coming the other way, colliding. They make a big spray of particles, but there's two very high energy particles emerging from the center. which are 2 photons. So what I do is I select all the events that I find, all the collisions that have 2 photons in them. And I then calculate the sum of the energy of the 2 photons. And I put them on a plot. So here's the sum of the energy of the 2 photons, and this is how often I saw that energy. So each event is a collision, and that's how often I've seen that a collision with 2 photons with a particular energy. And what you see is there's many different, this happens fairly frequently. I see lots of different 2 photon events all over at various energies. But remember the Higgs mass, the Higgs, if it's a particle, it has a specific mass. It has 1 mass value. And so then the energy of the 2 photons that it decays to should be 1 mass. And so what you see is here's the energy. This bump is due to the Higgs particle. So the rest of this is just other ways to make 2 photons. They don't prefer any special value of mass or energy, whereas the Higgs, because it has a specific mass, always decays to the same energy. The sum of the 2 photons is always going to have the same energy, and so you see this bump here. And that excess is what's telling you that there's a Higgs particle. Okay, I just said that. Okay. So now I've told you there's other ways, and I can show you in the backup, but in the interest of time, I've only told you one of the 3 ways that we've seen the Higgs so far. So now I want to talk a few minutes about the future. So the first big question that's left to answer is that the Higgs particle itself is an enigma. Quantum mechanics tends to want to make the Higgs a very heavy particle, 10 to the 16 GeV, so much higher energy than the LHC could ever produce. But it's actually this light 125 GeV. So the reason that quantum mechanics wants to make it heavy is because what can happen in quantum mechanics is this Higgs can come along, and remember, quantum mechanics can temporarily violate energy. A particle can go over a wall that it can go through a wall that it can't actually go over. And there's a similar process here where a Higgs can turn into a top quark and an anti-top quark, and then turn back into a Higgs. And these 2 guys can have any energy they want. And because they can have any energy they want, they will have the energy that we have to include in the calculation any energy up until we think our theory is still valid. So if I think my theory is valid to 10 to the 16 GeV, then I need to include all energies up to 10 to the 16 GeV. And if you do the math, it says, oh, the Higgs should be really heavy. But it's not. So one proposed solution is to add another kind of particle in here. This new kind of particle, it's called a stop quark. And it adds a new kind of loop that looks like this, that just happens mathematically, cancels that loop completely. And so this thing called supersymmetry is a proposed solution, and it's something that we're actively looking for to see if we can find. The thing is it turns out it can take many different forms, and so it's going to take a while to figure out if it's there and if we can actually find it. So this is one of the things we hope to find or constrain. Another big question is that we know there's something called dark matter out there. And the question is, can we make the dark matter in the lab? Because that would allow us to actually understand more about what it really is. So how do we know there's dark matter out there? Well, you know there's dark matter. The first evidence was by looking up at galaxies. If you look up at a galaxy, it's spinning. And if it's spinning, you know from simple classical mechanics that the faster things are spinning, the harder you have to pull them in to keep them in a circle, right? Like this woman here swinging a hammer. The faster she swings the hammer, that ball around on the end, the harder she has to pull in, right? So if she pulls that in hard, if it's spinning fast, I know how hard she's pulling in. Well, if you do the math and you look at how fast the stars are moving out here, we think that the gravity from all this other stars is what holds them in a circle, but it doesn't work out. There must be something else in here with more gravity pulling things in, because there's not enough bright stars there to be doing the gravitation that pulls the planets and stars at the edge in. And so people said, well, there's some matter there and it's not bright, so it's dark. But we don't know anything more about it than it's dark. And so that's called dark matter. Through history now, we have another way of knowing about it, which is a little bit more technical, which comes from the Big Bang. And if you look up in the sky, you can look back and you can actually see way back to about 10,000 years, or I guess it says 400,000 years, but a large number a relatively small number after the Big Bang, because right now we're at 10 billion years since the Big Bang, 13 billion years since the Big Bang, and here at only 400,000 times the Big Bang, you can see light from that point in time. And at that point in time, the universe was very smooth, and it only had little bumps. And if you change in the model, in the theory, how much dark matter there was, you change how many bumps you see way back in that time. And so we can look at how many bumps there are, and we can actually determine something about the dark matter. And the main thing we determined is that it's not a very light particle, or it's not a very fast particle. It's not like light, which is moving very quickly around the room. It's something slow, or so-called cold. So all we know now is from looking back there that they're cold. They're slow-moving particles. There's a bunch of them in this room, but we don't know anything more than that. There are a bunch of slow-moving particles in this room. Well, how would we know if we made it in the lab? The whole point of dark matter is that it doesn't interact easily with regular matter, because if it did, we would have seen it by now. And so it has to be invisible, which means we expect it to be produced in our detector, but run away and not be detected by our detector. So it can be produced in these collisions and then run away and not be detected. And if that's the case, how do we know it was there if we can't detect it? Well, you can know from momentum balance. So if I take two pinballs and I collide them and I make two pinballs coming out, okay, that's fine, right? Momentum is conserved. But if I collide the two pinballs and I see them all both on the same side of the detector, and I say, oh, momentum is not conserved. I put things in like this, and they came out like that. That doesn't happen in nature, right? If I collide two cars together, one's going to go this way, one's going to go that way. But if I see them both going the same way, I know something else went the other direction, and it's missing, and therefore I call that dark matter. I say something extra is missing. And so that's a way I might detect dark matter in the detector. Okay, the final big question is that we've talked about, we added this Higgs to the theory because we wanted to unify the weak force with electromagnetism. And already electromagnetism was the unification of magnetism, electricity, and light from special relativity. Well, we hope that there's more unifications in our future. There's a wide variety of theories about how those unifications might work. And we go out, and the best thing to do is to just look for signatures of those various ideas about how these unifications might work. And so we hope to go down this path until we get to a completely unified or a grand unified ultimate theory. So that's the final thing that we'd like to do. We don't know that this will be achievable with the Large Hadron Collider, but it might be. And so that we want to pursue that idea. Okay, so the summary is that we found the Higgs. It was 50 years of searching for it. These are 5 director generals of CERN who all contributed to planning into the LHC project, celebrating the discovery of celebrating the discovery of the Higgs in 2012. So we found the Higgs, and the future is bright.
Okay, do we have some questions? Questions from the audience? Students should speak up. Everyone understood everything? Let me ask you, okay, go ahead.
Find that missing energy in the detector. How do you determine if it's due to dark matter or
So this is a good question. So if I see that the missing energy that corresponds to, let me just go back so everybody sees this picture. So if I see this momentum imbalance, I have two particles come in, collide, and they go out the same direction, meaning that something had to go the other direction. How do I know it was dark matter and not neutrinos, which already I told you pass right through my detector in the whole Earth as well? And the only way we know is because we have a very good model of neutrinos, so we can calculate exactly how often we expect to see that happen. And we calculate exactly how often we expect to see the neutrinos, the effect from neutrinos, and if we see too much of it, then we know we've seen dark matter, so it's tricky. The further part of the question was, well, then how do you learn anything about what it was? I just know I saw something new and invisible. I don't know much. And in reality, it's not easy to tell, but once we say we saw that, we would begin to look at what comes with it. So we would begin to look in more detail, and there's many people are already looking in many different ways. We would look at what these guys are doing, and that might tell us a little bit about what this actually is.
in the diagram you showed before, the Higgs point to the
So the question is, what is the status of the theory beyond the Higgs? And the thing is that we don't have very much input information right now. So there's many theories, there are many ideas here that predict a wide variety of new particles coming down, from simple things known as Z primes, which often come with something called grand unification. Additional Higgses are possible. There's a wide variety of ideas about what could come. And they also have a wide variety of energies, only some of which are reachable by the LHC. So we are at a point where we don't have a lot of guidance from theory, and people are trying to piece things together. But the things I mentioned about dark matter and about this problem with the Higgs mass, these are our best guidances from theory. But you'll notice that they're fairly indirect. And so it's not clear exactly what energy we expect to see the new particles at. But we do hope that we find new particles and they begin to contribute to understanding how this fits together.
Yeah. What happens if you don't find anything of what you
So the question is, so we're going to increase the energy of the accelerator and in 2015, and then we're going to look for new particles. There's some hope that when we just cross a threshold and we suddenly start producing lots of new particles, if they're fairly heavy, it could be a big hit over the head, like, oh wow, look at all that stuff. There's also a very good chance that there isn't a look at all that stuff. So one of the things that we would want to do is we would want to go back and measure the pie chart in detail, because sometimes you can learn from this about things beyond the energy which you can achieve. So there are particular measurements here, like understanding the glue to Higgs production and the Higgs to gamma gamma and the ratios of gamma gamma to WW would give us some sensitivity to energies beyond the reach of the LHC. And so that's the kind of thing that we would be doing. Yeah, there's something right here.
So you said that you could possibly detect dark matter through a momentum imbalance, collision. But how would you distinguish a dark matter particle, say, from a momentum imbalance caused by just beams not being directly head on?
Okay, so the question is that if I see this momentum imbalance, how do I know it wasn't the beams being directly head on? So there's a wide variety of things in the experimental measurement that could lead to momentum imbalances, which we have to take account of. It turns out that the beams not being head on is actually a very small effect because we know the beam directions and energies pretty well. But there are other effects that are similar, just the quality of our measurements. The quality of our measurement, for instance, of the direction of the outgoing particles, the quality of our measurements of these guys could also lead to us falsely declaring that there was missing energy when there wasn't, or missing a momentum imbalance when there wasn't. So we have to do a lot of work in just understanding exactly how well our detector is working in order to do this. That's most of what we do during the day, is spend our time making sure that we understand how well building the detector, making it do this well, and then understanding how well it's actually doing it.
How do you look in different ways at the effects of things
Sorry, I
There's
didn't.
different ways that you can look at things that are displaced when you find something that, like, the momentum is a concern.
Right. So say I find this non-conserved momentum particle here, right? Well, first I would look at what kinds of particles these are, and then I would also look at things like what is the momentum of each particle, and that begins to tell. I can fit that through a theory to describe what might be the particle that's there. For instance, if I was producing a second heavy Higgs particle that was then decaying into a Z particle and a H particle, then what would happen is I would get a very specific momentum of these guys coming out. Whereas if they're not going through a second particle in between, then I'm going to get a very big, broad distribution of energies coming out. So it's kind of, there are ways to get effects like this bump that are more indirect than this bump, but similar ideas out from basically by looking at the momentum distributions of the particles on the other side.
One thing I'm just
The question. So remember. So when I introduced the dark matter, I said that the first evidence for it was that the stars were rotating too quickly on the outside of this to be due to the light, the stars inside, due to the gravity of the stars inside. So when that was the only evidence of dark matter, people tried to change the laws of gravity to explain this. And so so the question is, are we sure that that's not the case? And my understanding, and this is not completely my expertise, is that that is fairly ruled out largely by the cosmology experiments here, that you just can't have a modification that leads to the same effect here. And in particular, the bumps in the cosmological microwave background that I described, this light that's coming from the very early universe, and the bumps in them, is actually very constraining on the properties of this dark matter. In particular, if it was a light particle, like a neutrino, or like photons, if it was very light and moving near the speed of light, it would tend to flatten out all the bumps. So the fact that the bumps are not flattened out puts sort of a minimum mass or maximum velocity to the particles that are out there. And so we don't know a whole lot, but we do know there's a maximum velocity that they have. And so we have a little bit of constraint that way.
Any other questions?
Uh-huh. This one. Okay. There is any scale. It's just a cartoon, or it is a scale. For example, is it energy or something like that?
Yes. So this is a simplified version.
Question that Ames trying to ask this. Really, there is any hope that with accelerators going higher and higher and higher, it could go to explore the other points. So this is out of the question.
Yeah. So the question is right, as we went along this horizontal axis, this actually corresponds in general to going higher and higher in energy. And so the question is, how high energy do I have to go to get to these guys? And the general thinking is that they're very high energy, well out of the reach of accelerators, although there are a few ideas about how they could be within the reach of accelerators. But there's other interesting things that we can do. So we can actually look at the strength of the weak force, the strong force, and the electromagnetic force. And we can scale them up to that energy. And one of the things, another reason that I didn't mention that people are interested in this idea of supersymmetry, which solves this problem, is that it also makes it such that all those forces end up having exactly the same magnitude at this value of 10 to the 16 GeV. So at this very, very high energy, well out of the reach of any accelerator, these particles, all these forces would merge to the same mass. But in fact, in order for that to happen, we would have to find new particles at relatively nearby energies. So we have these sort of very indirect levers on things. There are other indirect levers as well. For instance, the proton lifetime allows us to probe energies that high. Because if a particle had a mass that large, it might allow for the proton to decay. And so people actively look for the first set of theories about what was going on here predicted the proton to decay at a fairly high rate, high enough that it was measurable. And then we went out and we measured the proton lifetime or put a limit on how long it is, because we'd never seen a proton decay. People put a limit on how long it is and said the lifetime has to be larger than this value. And that allowed us to rule out the first ideas about how this unification happened. So there are indirect ways in which we can access those energies, but directly colliding a particle at those energies, it's unlikely, but we don't really know where it is, but it's unlikely.